So we're going to study the logistic equation. It's easiest to start with exponential growth and decay. So exponential growth is a constant rate of growth. So you're going to times 2 and times 2 and times 2 times 2, right? That's why we have a growth constant that's always the same, but you're multiplying by the original, right? Original times 2, original times 2, so you get an exponential growth. The problem with this is that it doesn't model situations in the real world very well, like population, right? Is population going to grow in that manner? It can't. It just can't sustain it. Disease or lack of food or something will start to change that, right? So because of those issues, they come up with some other models. One of them is called the logistic equation. It's one of the very commonly used wildlife biologist population models. And it is very similar to exponential, except that it adds a factor in there that considers carrying capacity. Okay, so A is carrying capacity. If you're in a population model, Y will be the population at any time t. Okay. So what this looks like, we have a few different situations actually that can occur. You with me? I'm going kind of fast, sorry. Okay. So let's call this our carrying capacity, right? What happens if Y is greater than A? Population's above carrying capacity.
If Y is greater than, it'll cause a negative slope, which will mean the population will go down.
Right, we're going to come down. Optimally, the limit is this approaches infinity, t approaches infinity will equal A, right? The population will come to the carrying capacity. Okay, so that would be a calculus way to say that. Now we'll put Y here. Okay, so we can also have A equal to, or Y equals 0, right? That means there's no animals in population context. What happens if A is between 0 and Y? So if A is between, if the population is between 0 and the carrying capacity, what's most likely going to happen? Yeah, we're gonna start growing slowly, quickly, and then it's going to probably level off again to that carrying capacity, optimally. Now, things like drought years, predators, et cetera, will change that.
I think there's like almost a cycle where it'll go up like over the carrying capacity back
Yep.
down, and it'll just slowly start to reach the carrying capacity for a number of years.
Yeah.
That's still
Yeah.
affected by everything.
Exactly. Like realistically, we're probably looking at something more like, then it might come to carrying capacity, then it might dip, and then it might come up. I mean, realistically, those are some models that's probably what's going to happen, but very difficult to model that red line, obviously, right? Good luck with that. Is it realistic for A to be less than 0? Yeah. Right, there's no negative population, right? So we don't really worry about this, but the mathematically the model falls off, okay, if you do some work there. So that's kind of what the logistic equation is for. And what it gives us, okay. Since this is a differential, we can solve it in a general solution or a specific solution. So if we have this, can you separate those variables and solve the differential like we have been doing? Okay, the answer is yes. It's in your book. It's pretty nasty. It involves something you'll learn next semester called partial fractions. Okay, we don't have that, so I'm not going to lead you through it. Or you could just take the easy road and memorize the general solution, okay, which we put on the board already once, but it is right there, with the caveat that C that formula. Y0 is the initial value. Questions? Okay, let's use that. Would you write a new slide or under here? Would that be okay?
New slide.
Okay, hopefully it'll fit. Okay, solve. We'll just do a straight up math. dy dt equals 0.3y times 4 minus y. With initial condition. It's y0 equals 1.
Wait, where did A go?
Exactly. Good question.
Okay, it's going to be 1.
The carrying capacity is not 1. Okay, so one of the more common things that you see is that this doesn't match exactly the logistic equation, right? What we have to key onto is that this number right here needs to be a 1. That's what the formula dictates, right? So how would I make that a 1? Divide by 4, right? But if I divide one side of an equation by 4, it imbalances it, right? So to counteract that, I'm going to multiply this by 4. Okay? So that's going to be 1.2y. So I have divided by 4. In the parentheses. And I have multiplied by 4 here. To keep things balanced. This 4 divided by 4 is 1, right? Okay, so that's, now does that look like the logistic equation? Yeah, we're in good shape. We have A is 4, we have our Y's, and then K is 1.2, yeah? Okay, so now we can figure our solution based on that equation. A is 4. 1 minus, that is not a minus sign. E, and what's K? 1.2. And then we need to find the value of C, right? So what's our initial value? 1, right?
So even if it's like y at 1 equals something negative 1/3. So if it's like y at 1 equals something, is that still your initial condition even though it's not y at 0? Do that?
That's a good question. No. It has to be y at 0. Yeah. Yeah. So at time 0, what is happening? The deer population is 100. Okay. If you want to rewrite this, you can. Okay, a little cleaner. Okay, so that's just a general mathematical differential with a logistic equation in it. Okay.
Are these typically calculated experiments?
I would say no.
So are they an S for what y equals, or are they an S for?
Yeah, that if let's go through one where we can do that. And we'll put it into a deer population grows. Logistically, with K equal to 0.4, with carrying capacity 1,000 deer. The first question would probably be find the population P of T if the initial value was 100 deer. So, do you want me to write the differential out? Do we need to? Because you have, if you go back to your solution, we have K and we have A and we have Y0. We can just write this equation. Okay, so that's what we're looking for. So P of T equals, again, if you want to memorize this, just write it out every time. For the sake of time, we're not going to right now. A is 1,000 over 1 minus e to the negative 0.4 t, and c is 100 over 100 minus 0.4. Is that right?
1 minus 1,000.
Yeah, you're right. I knew something was wrong with that. It's not K, it's A. So, negative 1/9. So there's your population growth model. The solution to the differential, however you want to say it. We could ask something like, when is the population going to reach 500 deer? Okay, 500 is the population, and you could solve that equation. What a privilege, right? You want me to run you through that? You can switch these, or you can multiply that over and divide, it doesn't matter. But 1 plus 9, e to the negative 0.4t equals 1,000 or 500. It's 2, right? Subtract 1. Divide by 9. That looks familiar. So we get negative 0.4t equals the natural log of 1/9. And you can solve for t, right? That clock's off. The homework's posted on Classroom if you want to get, or I can write it down here. It's up to you. I'll give you till Friday. Does that sound good? Because we're just doing end of year tomorrow. So 9.4 is the section. Prelim 1 to 3. 1, 3, 5, 8, 9. And F, R, Q, B, C. 06. 4B. Okay, yeah, it is. I did update that yesterday.
Listen, David, did you guys use parts?